Let's check to see which of the following four choices are equivalent Boolean expressions. One way to do this exercise would be to simplify each expression using Boolean identities and then plug in all four possible ordered pairs to see if they work out to be equivalent. You could plug in the four ordered pairs immediately, but it could be a lot of extra work. It might be just easier to simplify them. So expression A simplified using the identities of Boolean algebra. I can factor out a not A. 1 plus anything is 1. Not A times 1 is not A. So choice A simplifies to simply not A. Next up to bat is B. Let's use the Boolean identities to simplify B, and here goes. First, I rewrite it over here. Now, be very careful here. Starting over again. This is not just your ordinary not a negative sign with the product AB. This is De Morgan's law applies. So the not of something ANDed with something can be rewritten as the not of the A plus, switching the multiplication here to the plus, the not of that B. Adding a set of parentheses just to be safe to that application of De Morgan's law and rewriting everything else. I have now, I can get rid of these inner parentheses. I can look closer at the middle here of this. Anything plus its opposite is always going to be a true. That's one of the identities. Rewriting everything else. A true ORed with anything, a 1 plus anything is going to be a 1. And not A times 1 is simply not A. So this expression simplified to just simply not A. And that is obviously equivalent to choice A. So those are both equivalent. They would not give you an exercise in which C and D are equivalent and A and B are separately equivalent to each other. That'd be too confusing. It would be ambiguous. You wouldn't know what the answer would be. So quite possibly C or D are going to be equivalent to A and B, or neither one will be equivalent. Let's work those out. Let's simplify those. Using, say, the color blue here for exercise C. Now C, I can apply the law, the identity of distribution here, and distribute that not B to those two terms. Oops, that's a B. And anything times its opposite here, B times not B is 0. A times 0 is 0. I still have a plus. B times its opposite here is 0, not A. Times that 0 is 0. Turns out that C is always going to be false. So it's not equivalent to A and B, because those could turn out to be true. If the A is false, then the opposite of false is true, and that would not be equivalent to a false. So C is not equivalent to A and B. It's not going to be part of the answer. Let's check to see if D is equivalent to A and B. D. Rewriting it down here, where I have room, be very careful. Because of Boolean algebra, this not could be applied to this a plus b, but it's De Morgan's law. So when you distribute that not to the a, you have to flip or change the plus to a multiplication. In other words, the or changes to and then that not applies to this b, and that's one variation of De Morgan's law. I'm going to keep a set of parentheses around this and rewrite this and proceed to the next step. The next step, you could use what I remember as FOIL. It's a variation, I guess, of the distribution identity. So this not a times this a can be rewritten here. This not a times that not b could be written this way with this plus. Oh wait, no, this is a star, not a plus. I thought they were both pluses. So ignore what I just said about FOIL or something like that. Let's just treat these as one term. I'll get rid of that star. So that one term there, that product, is being multiplied to this set of parentheses here. And now we can distribute this plus the product of those two. So rewriting everything, that's this times this, plus, then this times this. Going further, I could switch these around, the commutative identity, and then that a being right here, right next to that not a. Anything times its opposite is 0. This whole thing turns into 0 then, because 0 times anything is 0. And over here, the two not b's simplified to just one not b. 0 plus anything can be ignored. So d simplifies to this, which is not equivalent to these two. So the answer, which of the following are equivalent, would be simply the letter A and letter B. That's how I would show the answer on my ACSL test paper. Another way to have done this problem would have been to sort of make a chart of all the 4 ordered pairs, 0, 0, 0, 1, 1, 0, and 1, 1. Then carefully plug in each of these 4 into A. You would have seen that it's a true there, it's a true there, it's a false there, and it's false there. For B, you would have seen that anywhere that A is false, it ends up being true, and it's false otherwise. So because those two columns are equivalent in a one-to-one correspondence for all 4 ordered pairs, for all 4 possible, so this is an expression, this is choice A and this is choice B. These are variables A and B. If you would have plugged in C and D, C always works out to be false. We saw that here. And D, which is this equivalency, that is not a 1, 1, 0, 0. It's something else. So you could have also used a truth chart to have solved this exercise rather than simplifying the 4 expressions. So the final answer was A and B. This is equivalent to this.